session, we're going to look at total differentials, total derivatives, and total partial functions. In topic 5, where we looked at partial differentiation, we assume that none of the independent variables are related. We could state the equilibrium solution of the model in the reduced form, and by partially differentiating the solution, we could work out how an infinitesimally small change in a parameter or exogenous variable would change the equilibrium value of the endogenous variables. But to be able to partially differentiate, we have to assume that the independent variables are not related. So in other words, if x was to change, then y would stay constant, y would not change, and vice versa. So we were looking at a function like this, for example. If z is a function of x and y are independent, they are not related. Today we look at a slightly different situation where we would have, for example, z is a function of x and y, but y is also a function of x. So if x changes, that means that y is going to change. So clearly in this case, the independent variables are related. Similarly here, if z is a function of x, y, and t, and y is a function of x and t, if one of these change, then that is going to change y. So we need to find a different method that we can use in order to generate our comparative static derivatives. So if we work with this national income model here, where we've got income equal to consumption plus investment plus government spending, and consumption is a function of income and autonomous taxes, we will have two endogenous variables, y and c, and our exogenous variables will be I, G, and T. So we can reduce this model to this here, which would be an equilibrium condition, but we cannot isolate y on the left-hand side. That is due to the general form of the consumption function here. All right, so we're going to have to find or calculate our comparative static derivatives in a different way. So the way we approach this, we first assume that equilibrium income exists and that equilibrium income is a function of the exogenous variables. Okay, so we see that here. Equilibrium income is a function of I, G, and T, and we have this equilibrium identity here. Equilibrium income will always be equal to consumption at that level of income, as well as investment plus government spending. We cannot partially differentiate this identity to give us any desired comparative static derivatives. For example, we cannot work out how an infinitesimally small change in T would affect the equilibrium level of income. The reason for this is because the two arguments in C, equilibrium income and taxes, are not independent. They are related. Taxes is going to affect consumption directly and also indirectly through income. We can also think of it in terms of taxes affecting income directly and indirectly through consumption. To get around this problem, we need to use a technique called total differentiation. But before we look at that, we need to understand the concept of the total differential. All right, so the concept of a differential, up until now, we have worked with a function, for example, y equals f of x, and we have known how to go about calculating the derivative, which we can express using this notation or this notation. We are no longer going to think of dy over dx as a single entity, but rather as a ratio of two quantities. So if we do that, we can rearrange this here so that we end up with this here. Dy equals f prime x times dx. And we can think of this here as a converter that serves to convert an infinitesimally small change in x into a corresponding change in y. And dy is known as a differential, as is dx. So if we are asked to calculate the differential, if we are given a function like that, and we are asked to calculate the differential dy, following what we have written up here, we can see that in order to get this differential, we have to differentiate with respect to x. And we have that there, times by dx. Okay, so quite a simple process in order to calculate the differential. Just in terms of terminology, dy dx we know as the derivative, and we can think of it as the differential of y with respect to x, and differentiation is the process of finding the differential.